All right, so welcome to our review for exam number 2. So first we did chapters 22 and 23 together, basically. So this is the electric fields and electric forces chapters. So first thing we looked at was Coulomb's law, which says that if I have two charged particles, Q1 and then Q2, separated by a spatial distance of r between the two of them, this results itself in a either repulsive or attractive force, depending on the signs of the charges. But the structure of that force is then K, which is the electric constant, times the magnitude of Q1 times the magnitude of Q2, all divided by the distance of r squared. Where again, if I have like charges, this represents a repulsive force. So two positive charges or two negative charges. And if we have unlike charges, this manifests itself as a attractive force, where the direction of the forces are aligned along the lines that connect these two guys together. Now, if I have more than two charges, then the way we deal with that is we use the superposition principle, where the superposition principle simply says that we add all the particles or all the individual forces together on some particular force, and then the total force is simply the vector sum of all those forces together. So that would then be that what the force on the ith particle is then equal to the sum over all the jth particles of then the force on the ith particle by the jth particle. So this is the superposition principle. So good. Basically it. So from here then, we also talked about if we had continuous, but we didn't do much with that. I don't think we did any examples. So we're going to skip that. But then from there, we can move to electric fields. So then we defined that the electric field is equal to the limit as Q goes to 0 of the force per unit charge. So again, this is just how much force a charge would feel at a given point due to the presence of electric fields. But simultaneously, this thing also says that the electric force is equal to the charge times the electric field. So these two things work hand in hand with each other. So I can either define the electric field from this, or I can define the force from this. Great. So from here, we then look specifically at a point charge. So for a point charge, what we found then was that the electric field was equal to K times Q, little q in this case. That's what we use mostly notation in class. Little q divided by r squared in the r hat direction. Now, one thing I don't think I ever pointed out in class, but I'll point it out now because nobody ever asked. There is no difference between little q and capital Q. They're all basically the same. It's just the amount of charge. So good. So that's that. Otherwise, if I have a whole bunch of different electric charges and I'm looking for a particular electric field at a given point in space, in this case, again, we would use our superposition principle, which says that the electric field at a given point is simply equal to the sum over all of the particles which are contributing to the electric field at that given point. And so again, this is our superposition principle. Now, if I have a continuous object, in this case, again, all we're going to do is take that object and chop it up into a whole bunch of small dqs, and then find the electric field from each one of those different little dqs, and then again, vector sum them all together, which says then that the electric field at a given point for a continuous charge distribution is then again K, which is our electric constant again, integral of dq divided by r squared in the r hat direction, where dq, again, we write this in terms of a geometry integral. So this is going to be either lambda dl, eta dA, or rho dV, depending on the type of symmetry that I have. So again, if I have a line symmetry, I would use the first one. If I have an area symmetry, I would use the second one. And if I have a volume symmetry, I would then use the third one. So by their definitions, lambda is equal to the charge per unit length. Now, this is when it's equal to a constant. If it's not equal to a constant, it still has the same meaning. It's charge per unit length, but it's just not given this way. Eta is equal to the charge per unit area. Again, when it's constant. If it's not constant, again, it just has the same meaning, but it's just not given the same form. And then rho again is the charge density. So this is the charge per unit volume, again, when it's equal to a constant. So again, here we split this thing up into a whole bunch of different, again, DQs, and then found the meaning of R, looked at the direction of the electric field. Do we have to need the cosine portion, the sine portion, or all of it, and etc. So that was that guy. So some notable electric fields we found here, or at least some ones we should know, would be what the electric field of a plane. As we talked about in class, this guy then is equal to eta divided by twice of epsilon naught, where the direction is perpendicular to the direction of the plane. So this would be the direction of my electric field. So it's the electric field of the plane. So let's say that for now is the z direction. So this would be, say, for example, in the k-hat direction, but it just depends on how it's actually oriented. So if I had a parallel plate capacitor, for example, where I know this one has a plus charge, this one has a minus charge, and this one has an electric field which points this way from the positive. The negative has to have the electric field pointing into it, so it'd be pointing in this direction. So the two fields are in the same direction, but since this has no spatial orientation, that means I would just add the total electric field on the inside, so that the total electric field on the inside would simply be twice of that of this guy, of twice the plane, which means this would then be equal to eta over epsilon naught, and for example, again, the k direction. The other ones, it wouldn't hurt writing them down, but again, just note where they actually come from. So for example, if you want, you can write down the electric field of the ring. So you can write that one down. That's probably the one I would write down. So the electric field of a ring. All the other ones, again, just make sure you understand how we actually got to that particular results. Great. So what are some other things we talked about? So we also talked about dipoles. So let's again talk about an electric dipole. So an electric dipole is, again, I have two charges. I have a negative charge and I have a positive charge separated by some sort of distance d. So we define the d vector then as the vector which points from the negative charge to the positive charge. So this is my d vector. And then the dipole moment points in the same direction as d, where the dipole moment then is equal to the charge of the positive charge, q, times that distance vector d between the two of them. Right. Now, if I put this into an external electric field, so if here's my electric field, and then here is my dipole pointing in this direction with an angle relative between the electric field and the dipole, what we found is that this thing has a torque, where the torque then is given by the dipole moment crossed by the external electric field, which means then that the magnitude of the torque is then equal to the magnitude of the moment times the magnitude of the electric field times sine of the angle between the two. This also has a potential energy associated with it, where the potential energy, the electric potential energy, is then equal to negative of the dipole moment dotted with the external electric field. But the dot product is simply the magnitude of the moment times the magnitude of the electric field times cosine of the angle between the two. So this is the potential energy of the dipole moment in this external electric field. So that's pretty much it. So wasn't actually too much in these chapters. Most of it was just application. So finding the electric field from continuous and then doing a whole bunch of different examples for, again, my forces. So between superposition and then this one here. So that then brings us to chapter 24. So chapter 24 is Gauss's law. So here we define that the electric flux, this one. Good. So we said the electric flux was equal to, for us, what we care about is electric flux through a three-dimensional surface. So this is the closed surface integral over the surface area of that surface, then the electric field dotted by the differential area. So this is then, again, the electric flux. Gauss's law then says that the electric flux is then equal to the charge enclosed divided by epsilon naught. So again, the charge enclosed inside of some sort of hypothetical object. So here we get to choose the object. The point is to choose the object with the symmetry that matches the amount of charge, which means that the only symmetries that this is going to work for are number one, again, spherical symmetry. Number two, cylindrical symmetry. And number three, planar symmetry. So from here, the only thing I need to know are the surface areas for each one of these things, as well as their volumes. So whenever I have spherical symmetry, in this case, my surface area is simply 4 pi r squared. And then my volume is equal to, of course, 4/3 pi r cubed. And if I have cylindrical symmetry, so for cylindrical symmetry, depending on what I'm looking at, so the surface area for the shaft is equal to 2 pi r L. And the surface area for the end caps is just a circle. So this is then simply pi r squared. The volume for this entire thing, of course, is just the end cap area, which again is just pi r squared times the length of the object. So this is then pi r squared times L. Right. So here, typically, the biggest problem again is Q enclosed. So what's Q enclosed? So for example, Q enclosed is equal to 0 if I have a conductor, or it's simply equal to the charge density times the volume enclosed if I have a uniform density. And it's equal to the integral of the charge density integrated over the volume if it is not uniform. Now, of course, here I'm only looking at three-dimensional objects, right? But as we saw one example in class when I was looking at the line charge, in this case, it's still the same way. I'm just going to replace then rho with lambda and then V with L. Okay, so for example, so that's it. So it's basically Gauss's law. So again, here, the left-hand side, again, as long as I choose the correct symmetry, the left-hand side here is just going to become E times A, where A is just going to be the surface area. Again, as long as I have the correctly chosen Gaussian surface. So in that case, this guy is just going to become E times the surface area, which again means most of the complication is just going to come here. So that's about it. So that's all Gauss's law. So not too much in Gauss's law. So all we did was pretty much get applications of Gauss's law, as well as try to understand what we were actually doing. So finally, that brings us to chapter 25. So chapter 25 then says that what? The work done by the electric field is equal to negative Q integral from A to B of the electric field dotted by the differential length. Okay. Which is equal to negative the change in potential energy. Actually, sorry, it should be positive here. So work is equal to this, which is equal to negative of the change in potential energy, which in this case is the electric potential energy. So good. So in the case if the electric field is equal to a constant, this thing, of course, simplifies down to the work. The electric work is then equal to Q times E times D. So indicates that the electric field is constant, but again, in general, this is when it's non-constant. So here my electric field is not equal to a constant. Great. So from here, we can then define the electric potential, or I'm going to write the voltage, which is, again is the potential difference, is then equal to the change in potential electrical potential energy per unit charge. And then following what I have up here, this then is going to be equal then to a negative the integral from A to B of the electric field then dotted by the differential length. All right, so this is my electric potential. Now again, if I use this, so if I have a constant electric field, what this then tells me then is that my change of potential is then going to be equal to a negative the electric field times the distance. So this one is my relationship between the electric field and the potential. Again, assuming I know the electric field and I'm looking for the potential. Now, if I look at it the other way, then the electric field I can find from the potential. So if I know the potential and looking for the electric field, would be found by simply taking the derivative of all sides of this, which is then equal to the gradient of the potential, or in terms of derivatives, this is then negative the partial derivative with respect to x of the potential in the I-hat direction, minus the partial derivative of the potential with respect to y in the j direction, and then minus the partial derivative of the potential with respect to z in the k-hat direction. Good. Now, from here, we can then look at the potential of a point charge. So let's look at point charges. So for a point charge, this then tells me that my potential at any point is then equal to KQ divided by R. Okay. Now, again, this is technically the potential difference between the point R and spatial infinity. So if my charge was sitting here, so this is my charge Q, and this is my point R, distance away, then this is the potential at this point relative to this point out here where R is equal to infinity, where the potential is equal to 0. Okay, so remember, this is technically a voltage. This is technically a potential difference, but we just call it the potential at that point. Good. Now, again, if I have a collection of particles and I want to know what is the potential at a given point from that collection of particles, again, we're just going to use our superposition principle, which says then that the total potential at that point is the potential from each individual particle summed together. Now, again, here, the nice thing about this is, again, it's not a vector summation. It is simply a scalar summation. So it means I don't have to worry about directions and all that kind of good stuff. The only thing I care about is what's it actually doing. Okay. So again, going back to what we were done before, so what this means then is that the work to assemble a charge configuration then is equal to negative the change of potential energy. So again, this is equal to the work done by the electric field, which is then equal to negative of the charge times the change in potential. So again, here, this is just going to be the final potential minus the initial potential. So that's pretty much about it. So that's all the things that we did. So not too bad, not too many different things. So let's talk about what to actually expect. So as I said in class a couple times, so one thing that's definitely going to show up as a long problem would be this stuff here. So this would definitely be a long problem. So let's call that long problem number one. So one thing I'll say, pay attention to here is, again, is that lambda and eta and rho do not have to be constants. These guys can be functions of positions, which means that when you write this out, you can't automatically factor out the lambda, the eta, or the rho. You would have to keep it in and actually integrate, but you would have to know the actual functional form of those things. So and you have to know how lambda is a function of position, eta is a function of position, and rho is a function of position to actually be able to do this integral. Right, so this is definitely going to be a long problem. So other things we talked about, we also said that Gauss's law was definitely going to be a long problem. So all of this page then would be long problem number 2. Cool. So that's our Gauss's law. So what's the third one? So the third one then is going to involve something with forces. So the third one, so something with either forces from charged particles or, so again, superposition here, or other types of forces. So So this would be long problem number 3. So this one means that I would know, say, the electric field, and then I would put a charge in it and then see what happens. So an example of this one would be, again, the parallel plate ones that we did. So here we had the parallel plate, the charge moving into the plate, which caused the deflection. So this calls the deflection of delta y. So that's a good one. So here we know the electric field, say, is pointing in this direction, and it's a positive charge moving in. Or, for example, I could put a charge into an external system. So, for example, I could have a ring here, and then I could put a charge above that. So in this case, I know the electric field of the ring. So then I can find the force on this particle because of that ring, etc. So this is definitely going to be the third long problem. Now, in this long problem, there may or may not be some stuff with potentials. So basically, if I was dealing with point charges, this could be part added to that particular problem. So this might be, again, part of long problem 3. Maybe. We'll see. I don't know. I haven't quite decided yet. All right, so that basically leaves everything else. So for example, well, again, this stuff here would be part of this. So good. So that basically leaves that everything else then is going to be a short answer. So definitely dipoles. This stuff here would be a short answer quick calculation problem. So this would be short answer quick calculation number 1. For example, oops, I forgot that started the dipole. That should be part of it. Also things with like potentials. So for example, superposition and work, all this stuff would be a short answer quick calculation problem. Number 2, good. And what else do I have on there? Good question. I changed things around. So probably, let's say, superposition of electric fields, for example, also be another short answer quick calculation problem. So we'll look at things like that. So yeah, so that's about it. So like I said, so definitely one problem is going to be you have some continuous object. In this case, you have to integrate over the geometry of it to then find the electric field at a given point. Definitely Gauss's law, again, is going to be one. Now, again, how do you distinguish when to do Gauss's law and when to do Coulomb's law? Well, again, Gauss's law requires perfect symmetry, which means if you had a finite shaped rod, for example, and you're looking for the electric field at some point from a finite shaped rod, this doesn't work for Gauss's law. Again, the rod has to be infinite in length. If it's not infinite in length, if it's a finite length, Gauss's law will not work in this case. This does not work. No Gauss. Which means that if that doesn't work, that means I have to use this. So in this case, this does work for a finite shaped rod. This does work for like a square area or rectangular area that I'm trying to find the electric field for. So anything that is not perfect symmetry, so meaning if it was planar symmetry, it has to be infinite in length. If it's cylindrical symmetry, it has to be in length. Anything like that has to be done by Coulomb's law. If it's something like a sphere, or if it's a rod which has infinite length to it, a plane which has infinite length to it, in that case, you can use Gauss's law. So this is how you would distinguish when to use the one versus the other one. And again, the last problem is going to be electrical forces. So it might be electrical forces between point charges. So for example, superposition, where I have a whole bunch of different point charges and I'm looking at forces. Or I have something like this, which is something moving in an external electric field and then find forces, maybe deflections or different things like that. All right, so this would then be the third problem. Again, for the short answer ones, we're definitely looking at dipoles, so putting dipoles into external electric fields, looking at torques and energies, things like that. Again, for the next one, superpositions from the potentials we were looking at. So in this case, it would be from point charges. So have a bunch of point charges, find the potential at a given point, what's the work done to create that, and etc. So that's about it. So it's Not too bad. So what makes this exam more difficult than the first exam is now we're still dealing with the concept of fields, trying to understand fields. So it makes it a little more difficult than what it actually is, but technically this shouldn't be too bad of an exam. So most things are going to be pretty straightforward. So anyways, so same thing as always, if you have any questions, just let me know. I'll try to answer those right until we get to the exam. So also same thing, it's the same structure as last time. So you have the 3 short answer questions, you choose 2 of them, you have the 3 long questions, you have to do all 3 of those. There will be an extra credit on there, so you can do that as well. You do get the note card. Again, the note card is both front and back with all of these things on there, and then whatever, any notes and stuff you want to put on there to yourself. So that's about it. So yeah, just let me know if you have any questions.